So the main thing you want is, in statistics, is hypothesis testing. The main use of the scientific method and it's amazing, it's especially in, for example, drug companies, it's amazing how late scientific hypothesis testing became the norm in drug testing, for example. It's like 30 years. In the 1980s, you could just put out a drug and, as long as it doesn't kill people immediately, you put it out and then some doctor says, well, I think this drug does well. At least that's what I see in my patients. Like, they didn't have to do massive studies and actually test some hypothesis empirically to determine whether or not the drug helps or doesn't help. Okay? So what is hypothesis testing? You have a hypothesis. What's a hypothesis? Lesson. What's a hypothesis? An educated guess? Yes, well, it could be it doesn't have to be that educated, but a guess. Grant, did I see your hand up? Yeah? Arnav.
The default assumption?
An assumption, yeah, it's just a statement of fact. It's a fact. A hypothesis is a fact. It's a fact that is either true or false, okay? Either true or false. And you're trying to figure out, is it true or isn't it true? Okay, so here's a hypothesis. The number of people, let's see, I have good, let me write up a good, okay, here's an easy one. For example, this coin is fair. That's a hypothesis. That's either a true statement or a false statement. What does that mean, this coin is fair? The coin, i.e., the coin is a Bernoulli random variable with some parameter theta, and the statement that it's fair is if the parameter is a half, okay? So you can have a hypothesis, the coin is fair. You can have an alternative hypothesis, the coin is not fair. There's a word for these things, so I wanted to say this now. Let me just say this now. A hypothesis is simple. Let's talk a little bit about hypotheses, and we'll get to simple or complex. So what people figured out, this is very important, they started doing hypothesis testing in the same way as the US legal system. So hypothesis testing, you are innocent until proven guilty. So innocent until, this is the motto, until proven guilty. So what you want to do is you want to set something called a null hypothesis. Null hypothesis, usually written H0. And the null hypothesis is typically, there's nothing to see here. The coin is fair. There's no bias. This drug doesn't actually help. And what you're hoping is to reject the null hypothesis. Okay? The null hypothesis is the thing is guilty. There's nothing to see here. Nothing to see here. Coin is fair. Well, maybe you're trying to prove the coin is fair, and then your null hypothesis should be the coin is unfair. But that's...
There are like infinitely ways that it can be unfair.
That's right. So that's the difference between a simple or a complex hypothesis. We'll get to that in a second. So there's nothing to see here. The coin is fair. This drug doesn't help. Does not improve outcomes. That's a typical null hypothesis. Okay? So if you're going to test that hypothesis, you're going to test it against an alternative hypothesis. So you test H0 against, the terminology is alternative hypothesis. Alternative hypothesis. H1. Now, this does not have to be just the negation of the null hypothesis. So this is not necessarily, it can be, but you'll see some examples in a second. So this is not necessarily the negation of the null hypothesis. So let me give you a very particular example. Okay, let's just see an example right away. Example: you're a drug manufacturer, pharma manufacturer. You know that the proportion of the population that gets a disease when exposed to a virus, that gets a disease when exposed to a virus, is 90%. Okay? There's some disease, it's very bad, you want people not to get it even if they get the virus. So a virus enters your system, right? Common cold enters your system. If you have the vaccine, there should be a very low probability that you get let's say a flu, right? Do you guys know what's killed more human beings in the last 200 years, say, than anything else? It's not 9/11, it's not World War II, it's not World War I. It's not heart disease, amazingly. Flu in general. The flu has killed more human beings than all the wars, all the famine, all the heart disease. The flu just kills. Okay? We don't think about it because it doesn't kill us because we made it, right? It kills old people, it kills young people, it kills poor people. You guys are here. Didn't kill you. Okay, that's the survivor. You know there's all these great stories. You know the one about the airplanes that kept coming back in World War II? And they had all the bullet holes in the sides and in the wings, and they said, we need to fortify the sides and the wings to fix the bullet hole, you know, so that the planes. And what did the statisticians say? Yeah, it's the part where you don't see the holes that you need to put the extra metal in, because those are the planes that aren't coming back, right? So if it doesn't feel like the flu kills a lot of people, it's because you know people that survived the flu. Okay, so there's some virus, and it kills 90% of people that are exposed to it. In some places, that is the reality with the flu. They want to test, so they want to test the hypothesis that their drug improves on this, so decreases proportion of disease on exposure of diseased people to 60%. So your null hypothesis is that the drug does not help. Okay, so what are your variables? What are your random variables? Are our random variables normal? So we have, what's the population? Ernest.
Bernoulli.
It's Bernoulli. Population is people exposed to the drug. Okay? So before we get to this, population, people exposed to the virus. People exposed to the virus, well, and given the drug. And given the drug. The hypothesis, the null hypothesis is the drug didn't help. If the drug didn't help, then we still expect, well, hopefully it didn't hurt, right? If the drug is killing people at a higher rate than the virus is, that's really bad, which also happened in the history of drug testing. So that's why we use animals today. So, you know, with apologies to PETA, the alternative to killing animals for research is killing human beings, or not having drugs. So there's all kinds of. This is not a morality class. We're just statisticians. Population, people exposed to the virus and given the drug. The null hypothesis is that it doesn't help. So this random variable. So the drug does not help. The drug does not help. So our random variables are Bernoulli. They have some parameter theta, and if the drug doesn't help, then it's still 90% fatal, or 90% disease. Let's not make this about fatalities. How many, even if you don't die from the flu, you don't want to get it. It's annoying, right? 2 weeks of coughing and sneezing, whatever. So the null hypothesis is that the drug does not help you each of your random variables is still a Bernoulli with prevalence proportion with parameter 90%. The alternative hypothesis, H1, alternative hypothesis, well, you could say it does help, and then you would want to know that theta is strictly less than 0.9. But you see, that's going to be very difficult to test. Because the difference between 0.89 and 0.9, statistically, you're not going to come up with a test that can distinguish those two microscopic distinctions robustly. So let's pick a nice range where we should be able to distinguish them. The alternative is that the xi's are Bernoulli with, let's say, theta equal to 0.6. Okay? So we're going to test the hypothesis that the drug decreases the proportion of the diseased population to 60% of those exposed to virus. Does everybody understand what we're doing? So this is what I mean by the alternative hypothesis is not just the negation of the null hypothesis. It's some specific distance from the null parameter to the what you hope is the alternative. You hope your drug actually helps. And if it helps, then it should, help bring down the proportion of people that get the disease.
But in any case, we're sure it's Bernoulli, right?
Well,
okay, we want to believe we're sure.
We're gonna treat individuals
as random.
Yes. We're not going to take into account their actual family history, their age. Old people die from the flu a lot more than, okay?
Yeah.
So their IID, that's a huge assumption. Yes, and they're independent, although genetically they may be more predisposed to some things than others. So this is a major assumption, and you guys should be aware of that when you're making such assumptions. It's in some cases it's okay, or it's not okay, but you can't do any better. This is the best you can do, okay? So you should be very well aware of what assumptions you're making. We're making the assumptions that every human being in our population has the same probability of developing disease when exposed to the virus. We're going to give them all the drug, and we're going to test whether the drug has actually helped. Okay. So what your pharma guy says, you're in the boardroom, and they say, here's how we're going to test this. Here's our test. Let's give 20 people the drug. So that's our value of n. And we will reject the null hypothesis. We will reject H0 if the number, so let's say k, is the number that gets sick, the number that get the disease, is, let's say, well, so 90% of 20 people is 18 people. So your pharma guy says, let's say if at the most 14 people get sick. Doesn't have to go all the way down to 60%, well, right, so 60% would be 12. Doesn't have to go all the way down there. We're just going to reject it if we get down to 14. Okay? You're developing this test. We're going to give it to 20 people. We're going to say, yes, we should reject this null hypothesis in favor of the alternative hypothesis if fewer than 14 out of these 20 people get the drug. Okay?
Why 14?
They made up a number, something in between. What we're going to do, we the statisticians, analyze how good of a test this is.
Oh.
Okay? All right? So, our job, they have decided on this number. In a minute, we're going to turn it around. We're going to say what the right number is that makes the test as good as possible. But the first approximation to that is someone has decided this is the cutoff range. By the way, that's called the critical region. Definition, the critical value, sometimes critical region or value is the set of outcomes for which we reject. we reject the null hypothesis. Okay? So, the question is, how good is this test? Evaluate this test. How good is this test? Now, what do we mean by how good is this test? Okay? Well, there are a couple things that could happen. So here's a kind of elementary box chart of what could happen. What could happen is, bless you, h0 could be true, and you could accept h0. By the way, accept is a terrible term, as you'll see in a second. That's one of the things discussed in this Nature article. Not reject. Fail to reject. Okay? So fail to reject would be a much better term. Fail to reject h0, and h0 is true, then you have not made an error. Let's say h0 is false. We're trying to see, is h0 true or false? Is null hypothesis true or false? Here's what happens if you reject h0. So if h0 is false and you reject it, that's again not an error. You've correctly identified the truth. You've rejected h0, and indeed h0 is false. Two things could go wrong. You could reject h0 when it's true. There's a terminology for this. It's called a type 1 error. Type 1 error is reject h0, but h0 is true. There's a type 2 error. Now, type 2 error is slightly subtle. You see, this is an actual dichotomy, but we're not testing h0 as false. We're testing whether h1 is true. We're going to have h1 as the alternative to h0 being true. So if we fail to reject h0, okay, so the type 2 error is we accept h0, but in fact h1 is true. So our job, the way we're going to answer this question, how good is this test, is to compute the probabilities of these two types of errors.
Is there any good way to weight them nicely?
That is a
That's it.
subjective thing, depending on how much you're concerned about each type of error. Okay? So now we're going to analyze them, and then we're going to see various.
So type 1 is false positive, and type 2
In a sense. If positive means the rejection of h0. Positive, you want to reject h0 if that's the kind of, if you've set up the null hypothesis the way it's typically set up. So that would be a false positive, this would be a false negative. Okay? And typically the probability, so just some more, the probability of a type 1 error is typically written alpha, and the probability of a type 2 error is a lot of times called beta. These are just names. So let's compute, in this case, the probability of a type 1 error. So probability of type 1 error. This is alpha. What does it mean that we have a type 1 error? That means that's the probability that h0 is true and we reject h0. Remember what h0 is. h0 is that the xi's are Bernoulli with theta equal to 0.9. So that's the probability, assuming theta is equal to 0.9, that we have a sum of Bernoullis. Where are we? Can you see all of this at once? Not really. How's that? A little better. And a sum of Bernoullis, remember a sum of Bernoullis, what is a sum of Bernoullis? Binomial. So it's not the average, but n times the average is the binomial, because the average you divide by n. I don't want to divide by n, I just want to sum. And this is at most 14. Okay? So this is a Bernoulli random variable sorry, this is now a binomial random variable. N times x bar is a binomial random variable with theta equal to 0.9, and we want to know what's the probability that it's below 14 out of 20 outcomes. But we know how to do that. So what's the probability of each Bernoulli outcome? I keep saying Bernoulli when I mean binomial. What's the probability of a binomial outcome? What's the density?
20 choose k.
Right? 20 choose k.
0.9 to the k.
Theta to the k, 0.9 to the k, other than Ernest.
Minus
0.1
0.1. 20 minus k.
to the 20 minus k. That's the probability of each k, and the k's that we are interested in are the ones that go from, yeah, or 0 to 14. Yep. Does everybody see that?
Why 0?
Well, because it could be that none of the people get sick. The drug could be so good that of the 20 people, none of them get sick, even though theta is 0.9. So this you plug into a calculator. You plug into a calculator, and you know what comes out? 0.011. So alpha is 1.1% in this case. So alpha is 1.1%. For whatever reason, historically, people have taken 5% to be significant. So 1.1% is an excellent fail rate for rejecting the null hypothesis. Okay? I don't know if you would want to, if you're playing Russian roulette and you're spinning a gun with 100 chambers, one of which has a bullet, I don't know that any of you actually want to play that. So keep in mind what that 1.1% might signify.
Wait, so is that the p-value?
Not yet. We're getting there. We're getting there. At the moment, we're evaluating. So the way to answer this question, how good is this test, the test that we've devised, is to determine the size of the type 1 error, which is called the size of the test, and the probability of the type 2 error. Okay. So this is let's put in this is the size of the critical region. Critical region. Just terminology. It's also called the level of significance. Level of significance. Okay. Let's work out the type 2 error. So beta is the probability of a type 2 error. So what is a type 2 error? Yes. Tell me your name. Saji.
For the critical region, we defined it as a set of outcomes for which we reject the null hypothesis.
Yes.
Wouldn't that be for both cases when
Yes.
zero is true and false?
That's why it's in quotes. This is what people say. When they say the size of a test or the level of significance of a test, they mean what is the probability of a type 1 error. Yes, it's not literally the probability of the critical region, because the critical region by definition is the set of outcomes where you reject, not when you reject assuming you shouldn't have. Just what's the set of outcomes on which you reject. This is what human beings decided to call these things. Sorry. Other questions? So far so good. Does this make sense? This can be very confusing. In fact, looking at the book, I would be amazed if someone could really unwind what's said there. But hopefully this is making some sense. Okay, so what does it mean to be a type 2 error? That is when H1 is true, right? H1 is true, not H2, and you'll see why. You'll see immediately why it's convenient to have this alternative hypothesis, because you're going to want to test it in this kind of very precise way. What's the probability that H1 is true, but you've accepted, that's this error, but you've accepted, and you accept H0. In other words, you're outside of the critical region. Okay? So what is that? So if H1 is true, what was our H1? Yeah, it's that theta is 0.6. So that's the probability that theta is equal to 0.6. And, I mean, this isn't really a probability. This is just telling you, here's what our actual distribution is. And we accept H0. That means that the total number of outcomes is greater than 14. So at least 15. 15 to 20. So again, you set it up in exactly the same way. That's a sum. As k goes from 15 to 20, 20 choose k. 0.9 to the k. 0.6 to the k, because we're assuming that 0.6 is the correct theta. And what to the 20 minus k? 1 minus theta is 0.4 to the 20 minus k. Again, you put this in a calculator. Wolfram alpha. Did anybody do it? Ernest did it already. What is it?
12556.
12559 or something. Let's call it 6. Okay? So this is 12.5% or 12% crudely, almost 13%. So this test is a very good test at having a low false positive, but a rather bad test. 12% is way bigger than 5%. So it's a rather bad test at detecting false negatives. So you should be able to, with this test, with this critical region of 14, you should be able to, if this happens, you should have a very low probability of mistakenly rejecting that 90% is still the proportion of people that get to the disease. But you should not be so confident about your claim that then it's actually 60% of the people. That the drug is 60% efficient instead of 90% efficient. Okay? So what you might say to the board member is, well, 14 isn't the right place to make this cutoff. Maybe 15 is a better cutoff, or 16 is a better cutoff. You repeat these calculations, what happens? When you make this 16 or 17, this number goes down. When you make this 15 or 16, this number goes up. And it might be that there is no place in the middle that gets both of these numbers down to 5%, for example. There's an obvious trade-off between false positives and false negatives by changing the critical region. Does that make sense? What's a way of getting both of these numbers to come down, other than Ernest? Dylan?
Increase sample size.
Increase n. Increasing n is really the only way to get both of these numbers at the same time to come down. So if there's not a region in which both of these numbers can be taken down to 0.5, well, there's another thing you could do. You could change what your alternative hypothesis is. You could say, well, I don't think it's 60% effective. Let's say it's 70% effective. It's not that effective. Of course, you want to market. So for marketing purposes, you want to say, hey, this drug really works. Right? So there's all kinds of trade-offs here. Grant?
If you change the cutoff for 14 instead of 15, how much will that change alpha or beta? Will it be inverse or?
You mean the actual numerics?
Oh well, so if we're choosing the cutoff as 14, say we choose the cutoff as 13.
Yes.
12. How much will that change type 1 and type 2? Will bring them both down?
So let me say that again. If we make this 15 instead of 14, then we're adding one more term. That's increasing the probability here. We're subtracting one term here, so that's decreasing this probability. Okay? Does that make sense? Yasin?
In the premises, you said that we're trying to test whether the drug decreases the proportion of disease people to 60%.
Yes.
So why would that be 60% effective?
Well, it's not 60% effective. What our alternative hypothesis, you see where the 60% comes in is here. We made that number up. We made that number up. That's crucial to understand. We made that number up. The alternative is that only 60% get that. We have to have some reason for choosing that 60%. 90% is that's what we see in the population. People get it. 90% of the people that get the virus get the disease. This is what we think our drug is going to do, and let's test it as an alternative.
It's going to decrease the 90 to 60.
Right. We think the alternative is that when we give the drug, it decreases the prevalence from 90% of the population to 60% of the population getting the disease once they're exposed to the virus. Okay? if we make this number 0.7, it's maybe not obvious what will happen here, but in fact this will go down. Because 14, by the way, is 0.7 of 20. Right? But that's a weaker distinction between the null hypothesis and the alternative hypothesis. The alternative hypothesis has all of a sudden gotten closer to the null hypothesis. We're not saying that there's a gap, that there's a drop from 90% to 60%. We're saying there's a drop from 90% to 70%. The drug's not that good. Okay, so we decided this number 0.6. Does that make sense? Okay, so that's the first basic kind of calculation in hypothesis testing. How good is this hypothesis? What is the size of the type 1 error? What is the size of the probability of the type 2 error? Okay. Let's do another example. Let's do another example. So here's an example. You have a bunch of, yes.
Can you use this method for determining whether the distribution that you assumed that the population was actually the distribution that it is?
Okay, so that's much more subtle. We may get to that towards the end about determining whether, so Yas's question was, can we use this kind of analysis to say something about, you see, we've assumed that the population is IID Bernoulli with some uniform parameter among everybody, but actually that might not be true. There might be some other distribution that more accurately models this situation. There's a major theory of how to handle general distributions and to figure out what the right distribution is. Is it Poisson? Is it exponential? Is it chi-squared? Or where is this? Where does the data really belong? What's the parameter space? There's a whole big theory for that. We will eventually maybe get to that in this class, maybe not, depending on timing.
Well, is there a way to merge distributions so that it is IID, but for certain values it's going to be one distribution and then another, like a piecewise thing?
So, yes, and it's much more, so now we're getting to variational calculus. So variational calculus is instead of, do you guys know this Brachistochrone problem? No, this is totally off topic, but just so, it started the, let's take a minute. This is good stuff. So before we get to this example, sorry, Yas asked this question. So here's the Brachistochrone problem. It's a famous problem in the history of calculus. The Brachistochrone, this is the fastest time that a point that, I'm going to make some kind of track. I'm going to make a track. I don't know what it's going to look like. Maybe it'll look like this. Maybe it'll look like a straight line. Maybe it'll go down all the way and then across. So I want to get from point A to point B, rolling. So how fast, what's the path? What is the path? What is the path of best, shortest time, that's Brachistochrone, shortest time, for a ball to roll without, without friction or whatever, or without slipping from point A to B, using only gravity. So only gravity is acting on it.
So do you use Lagrange then or something?
That's where, yeah, Euler-Lagrange equations were exactly, so this is variational calculus. This is the beginning of variational calculus. Variational analysis is, instead of optimizing parameters, you're optimizing over spaces of curves. What are the possible distributions? What's the shape? If I think, the kind of question we're asking is the density, is our PDF, what's a PDF for a Bernoulli? There's a 0 or 1, there's some probability for 0, there's some probability for 1. There are delta spikes at these two places. Right? That's what it looks like. Or what's a PDF for a Gaussian? Well, it depends on what mu is, and it depends on what sigma is, right? This length is sigma. Those are the two parameters. But how do I know that this is the right shape for the problem? Maybe there's a completely different curve that more accurately represents the density, the distribution of whatever the underlying random variables are being sampled from. that exists. That's a fascinating topic, and maybe we'll touch on some aspects of it at the very end, but realistically, probably not. Okay, so we're stuck with parameter estimation at the moment. Maybe at the very end we'll have time for more general questions like actual what's the right density or spacing densities. These are just the ones that have names. I can draw anything that has integral 1 and call that my density function and see if what the right distribution is. Okay, so there's a massive theory here using techniques from variational calculus that maybe or maybe not we'll get to. Okay, let's get back to this example. So here's the example. We're going to have a normal population now. Again, that's an assumption. That's an assumption. I have my normal population, x1 to xn. Let's. This is a scientific study, so let's pretend we know. I mean, this is I don't mean scientific, academic. This is an academic study. Let's say we know that the variance is 1. And we're going to test the null hypothesis that the mean is, let's say, mu0 against, so we're going to test the null hypothesis against the alternative hypothesis that the mean is actually mu1. Okay? So let's determine yeah, so I wanted to say one thing before. I wanted to say that when the hypothesis, this is important, when the hypothesis completely determines the underlying PDF, where your random variables come from, that's called, that hypothesis is called simple. And if it does not, so that's, for example, the hypothesis that once you know that sigma squared is 1, mu is mu0, you've determined everything exactly. You know exactly the shape of this curve that you're testing. Okay? Otherwise, it's called composite. Otherwise, the hypothesis is composite. Hypothesis is composite. That's just the terminology. For example, if your coin, let's say, is unfair, but you want to test really how unfair it is, let's say you want to say theta is less than 0.4. Not theta is equal to 0.4, which would exactly determine what the distribution is, but theta is less than 0.4. Well, then I don't know what the distribution is. I have a range of possible distributions. Okay? And you can see how in the previous example we would not be able to test theta is less than 0.4 because we were putting in theta equals 0.4. Yes? PDF. Yes, this is meant to say PDF. And it turned into something else, PDF. Okay? So these are two simple, and the previous ones were also simple hypotheses. Everything is determined on the hypotheses. Ernest?
For your example, which one is larger, mu0 or mu1?
Yeah, let's say, let's make it mu1 is larger, whatever. Doesn't matter. Let's say mu1 is the larger one. Okay? We're going to test one hypothesis against another. So hypothesis H0, let's see what the distributions are. So here's mu0, here's mu1. As Ernest said, let's make mu1 larger. They have the same variance. I just don't know where the center is. Well, this is meant to be the center. I should have drawn the curves first and then the mean. Okay? So I don't know which of these distributions I should say the sample is coming from. So our question is, let me formulate it in a good way. Find, so here's the question, find a value of k so that the critical region, x bar is greater than k, is our critical region, has level of significance alpha. Has level of significance alpha. Let's say, just to make it concrete, 0.05. Let's unpack all these words. What does this say? What is level of significance? By definition, other than Ernest, tell me your name, Nikit. Type 1 error, okay? So I want to know that alpha is the probability of a type 1 error. What is a type 1 error? Justin? We reject null when it's true. Is rejected and true. Okay? So what is this saying? It's saying find the critical region for which we get a type 1 error of size alpha, 0.05. Okay? It's exactly what we were talking about in the previous problem, which we could do numerically, but let's do now kind of in general. So what does this mean? Well, if we reject it and it's true, so what does it mean that it's true? It's true, that means that the fact that h0 is true means that mu is m0. And we reject it, that means that x bar is bigger than k. That's the critical region, right? Where is k? K is going to be somewhere in between mu0 and mu1. So if we see an average that's bigger than k, right, we're going to test the average. We got a bunch of samples, x1 through xn. They're all Gaussian. They're all taken from this distribution. We're going to take the average, and we're going to see if it's bigger than k, if it's far enough away from mu0, right? K will be some number bigger than mu0. Then we should definitely reject mu0 as being the center with a type 1 error of size alpha. Again, let's unpack that. What do we know about x bar? If the xi's are Gaussian, mean mu0, variance 1, then what's the distribution of the sample mean? Normal. It's normal. What's its mean? Same mean, mu0. We're assuming that the mean is mu0. And what's its variance? 1 is the original variance, and when you sample a bunch of things, when you sample n things, Ernest?
1 over root n.
1 over root n is the standard deviation. Yeah. Do I put here the standard deviation or the variance? Sigma or sigma squared? Okay, sigma squared, which is 1 over n. Different. I forget which we use in this class. Different.
Okay, wait, so when you add them all up, you get variance n, and then you divide by 1 over n, but because you're doing variance, you divide by 1 over n squared?
Yes.
Okay. Then you get 1 over. Okay.
Yeah. That's another way of thinking of this. You add them all up, each one had variance 1, so the sum has variance n.
Yeah.
But the sum divided by n has variance 1 over n squared times n, which is 1 over n.
Okay.
Does everybody follow that? Okay, so that's its distribution. That's using this assumption, and now I want to compute the probability that x bar is bigger than k. So the probability that x bar is bigger than k, well, I know what that is. It's the integral from k to infinity of the PDF of x bar. The PDF of x bar is e to the minus, let's call it z minus, what's the average? What's the mean? mu0 squared over 2 sigma squared, that's 1 over n, normalized by 1 over root 2 pi sigma squared, dz. this is the size of the critical region. This is the level of significance. And we want to find a value of k so that this integral comes out to alpha. Does everyone follow this? Juliet, is this okay? Be honest. Yes?
Sure.
No, sure is not good enough. This is statistics. We need certainty in, well, not an experiment. This isn't an experiment, right? We need certainty and understanding. This is the PD. What is this? E to the minus z minus mu 0 squared over 2 sigma squared times 1 over root 2 pi sigma squared, where sigma squared is 1 over n. That's just the PDF of normal with mean 0 variance 1 over n Gaussian random variable. That's what x bar is. We've used the fact that mu is mu 0 to say we know exactly what the distribution is. And for some reason we knew that sigma squared was 1 of the original. Yes. Okay? So this is the probability. Now we have to write this. We're trying to solve the equation this is equal to alpha for k. K is the variable that we want to determine. We want to determine what's the average at which we should reject the null hypothesis. Kiana.
Can you explain the exponent of the exponential?
Yes, so this is just the general shape. This shape, this is e to the minus z minus mu squared over 2 sigma squared, where mu is mu 0. That's because we're assuming h0 is actually true. We've made a type 1 error.
So that,
And
that
sigma.
part that you wrote under there, that's part of the Gaussian Pdf?
Say it again?
That part down there, that's part of the PDF of Gaussian?
Yes, the Gaussian PDF in general is e to the minus z minus the mean squared divided by 2 sigma squared. That's just the general distribution of the Gaussian. It's normalized by 1 over root 2 pi sigma squared if you put the sigma inside the radical, or root 2 pi times sigma if you don't. Okay, so far so good? Now, we want to say this is equal to alpha. We look it up in a table? Well, we can't look it up in a table. It depends on what n and mu 0 are. So we need to convert this integral into an integral of a standard Gaussian. Then we can look up in the table what value of that standard Gaussian gives me the alpha that I want, 0.05. Okay?
We usually use z for that one.
Exactly, z. So we need to convert this in order to solve for k. We need to convert this to standard Gaussian, standard normal, so we can look up, or not look up, we still say look up in a table. I can't get away from saying look up in a table. Never look up in a table, just hit Wolfram Alpha or whatever, Google the value. So we can look up in a table the value of z alpha, right? Z alpha is defined by the integral from z alpha to infinity of e to the minus z squared mean 0 over 2 sigma squared being 1 over root 2 pi dz is equal to alpha. Okay? Does this make sense? So this is a number we can determine because this doesn't have any numbers in it that we don't know. Just an absolute equality. That's the definition of the number z alpha. So how can we turn this distribution? We have a minus z minus mu naught squared over 2n into e to the minus z squared over 2. We just need to make a change of variables. Okay? So what do you want your dummy variable to be? U? U? And I want, let u, so how should I set this? Well, what I want is that u squared over 2 is equal to what I have here. I want u squared over 2. That should be u squared over 2, but it isn't. It's this thing. It's actually this thing. To be z minus mu 0 squared over 2 over n. If you don't want to think about it, you just say, I want this part, which is supposed to be u squared over 2. I mean, if I had used u's as my dummy variables here, to be this exponential part, which in fact is z minus mu 0. Can you guys see this? Even in the back? You can still see it? Okay, you don't need to zoom in. It's a little blurry. Okay. Z minus mu 0 over 2 over 2 over n. I mean, it's a funny way of writing it, but I don't want to confuse you further with changing the algebra. So if that's the case, well, we can cancel the 2's. Let's take square roots, and let's move n to the other side. So that's saying that n u, I guess I'm taking square roots. So square root of n of u is equal to z minus mu 0. That's my change of variables.
What do you mean u squared over n?
It should be u over square root n.
Yeah.
Thank you. When I move this to the other side, it's a 1 over n. What I mean is to put the root n here. So now I am doing the algebra that I wasn't doing before. Put that over there. Or let's solve for z. U over root n plus mu 0 is equal to z. Bless you. Okay? So what is dz? Mu is a constant, n is a constant. dz is 1 over root n du. So let's put all of that back into our change of variables. This is equal to the integral. Let's worry about the limits in a second. I have my constant 1 over root 2 pi over n. I have an e to the minus. What happened to, the square is gone. What happened to e to the minus z minus mu naught squared over 2 over n? Z minus mu naught squared over 2 over n has become u squared over 2. Perfect, just as we like. What happened to dz? dz is 1 over root n du. And check out this root n in the denominator of the denominator, and this root n just in the denominator. They exactly cancel. So we get our beautiful standard normal Gaussian. Now let's look at this change of variables. As z goes to infinity, what happens to u? Goes to infinity. As z goes to k, this lower bound, as z goes to k, what happens to u? K minus mu naught times root n. And this probability needs to equal alpha. That's what we're trying to compute. We're trying to compute the value of k for which this integral, which was that integral, comes out to alpha. But we know how to make a standard Gaussian normal come out to alpha. You just need to start at z alpha. Kiana.
Can you explain the change of bound?
Yes. So our original bound was z starts at k and z goes to infinity. When z starts at k, u starts at k minus mu 0 times root n. And when z ends up at infinity, well, this is infinity minus a constant times a positive constant, still plus infinity is the upper bound. Okay? So now it's clear what to do. This thing needs to equal k minus mu 0 times root n needs to equal z alpha. That's what z alpha means. Z alpha means if you start here at any rate out to infinity of a standard Gaussian normal, you get alpha. So this lower bound needs to be z alpha. And now we solve for k. So if I divide by, so k will be equal to z alpha divided by this root n, and then I add mu 0 to it. So let's look back at the question. Find a value of k so that if x bar exceeds that value of k, the level of significance turns into alpha. This is the value of k. It's mu 0 plus some amount, but that amount gets discounted by 1 over root n. So if you take more and more samples, you have to make k less and less above mu 0, right? This value k is mu 0 plus something, and it's the value for which this, I sort of drew it in a bad place. Let's put k here. So that this integral is alpha. This is our like probability of failure, of type 1 failure. Ernest.
If mu 0 was greater than mu 1, would you just put the minus sign in front of the z alpha over square root n?
Exactly. If these were the other way around, if we were testing that mu 1 is less than mu 0 instead of mu 1 is bigger than mu 0, we would want to test that with an x bar being less than k, right? We're asking, where do I need to put my cutoff so I can be 95% sure, or I can have 95% confidence with the statement that I've correctly rejected the null hypothesis. I've not made a type 1 error. The probability of a type 1 error is 5%. What is z alpha for 5%? 1.6 something? 1.645. Okay? So you go from the expected correct mean out to 1.645 over root n. That should be where you catch this condition. The level of significance is alpha. Any questions? Are we done evaluating this test? The quality of this test? Well, we've answered the question. We've answered what value of k do we want if we want the level of significance to be 5%. But that hasn't told us whether mu 1 is a good alternative hypothesis. Okay? So our problem, part 2, is the alternative hypothesis a good hypothesis? Is this alternative good? In other words, i.e., so there's terminology for this. It's called the power. Let me give you that terminology. All right, let me just give you the terminology. Is this good? I.e., well, let's get there in a second. I.e., what is beta, the probability of type 2 error? So let me give you some terminology. Definition. How do I want to say this? All right. When testing H0, the alternative hypothesis, alternative H1, has power. This is just the terminology. The power of a test is 1 minus the size of the type 2 error. So the significance of the test is how often do I expect the type 1 error to occur, and the power of a test is how good is this H1. In other words, what's the size of 1 minus the size of the type 2 error? Does that make sense? So the test will have a type 1 error with 95%, will not have a type 1 error with 95% certainty, but that doesn't tell us if mu 1 is in the right place to have a powerful test for the alternative. It's just the terminology, two different ways of talking about the errors. One type of error is called level of significance, or the size. The other type of error is called the power. And you want the power to be large, so you make it 1 minus beta instead of beta. It's just historically what people call these terms. Okay, so let's determine the power. What is beta, i.e., find the power of H1, of this test H1. So let's do it. So how can we find the power of H1? What is H1? Other than Ernest? So what is beta? Beta is the probability of a type 2 error. You're going to get used to this. These words are they're brand new words today, but they will very quickly become ingrained in your head. Arnav.
So
So that will be the probability that mu equals mu1 and x bar is less than k.
Less than or equal to, less than, these are continuous integrals, makes no difference. Okay, Dylan.
In the previous equation, so if our sample is infinite somehow, would we reject HO
If our sample is infinite?
Yeah, like just like theoretically if it was.
Yes.
Then would we reject HO if k is equal to mu 0? Is that what that's saying now?
Well, I think if the sample is infinite, the law of large numbers tells you that x bar is going to mu 0. So whatever, if your sample really is actually infinite, then with probability 1, you can say that whatever x bar is, that's it, that's mu. This is always in the presence of imperfect information, not infinite samples.
Okay.
I don't know if I answered your question.
I think you did.
Yeah.
No, you're right.
Yeah, for infinite, I mean, there aren't infinitely many people to poll, or there's a finite number of elementary particles in the universe or something. I don't know. Okay, so what's the probability that mu is equal to mu1 and x bar is at most k? So what do you think that is? Should I give you a minute to think about what this actually says, Ernest?
Can you just skip to just saying like this is just the probability that x bar is greater than k, given that mu is equal to mu1, and then it's basically just 1.645 divided by the square root of that plus mu1.
Yes. Yes, I'm trying to give people another chance to redo the calculation that we did previously so that the previous calculation sinks in. You can do all of this, by the way, without going to the densities. I'm going to the densities because I'm trying to remind you of the underlying mathematics. So you're saying, why don't I skip to the part where
So you just standardize it?
you can just standardize it? I mean, that's literally what we, okay, let's do it the slightly simpler way without going all the way to the integral. Okay? So so this is the probability. So if I'm assuming that x bar, this assumption means that x bar is normal with mean mu1, not mu 0, and still variance 1 over n, which means that if I take x bar minus mu 1, and I divide by the square root of the variance, that will be a normal variable. And I want to catch this condition. Well, I'm going to have to do the same thing to k, because this is a monotonic function. That means k minus mu 1 over root 1 over n needs to have probability beta. Does that make sense? So this is, now we're doing something different. So this is now a Gaussian normal. This is now standard normal. Standard normal. We've subtracted off the mean. We've divided by the square root of the variance. We have a standard normal. And the condition that k bar is less than k is identical to the condition that, x bar is less than k is identical to the condition that x bar minus mu1 over 1 over root n is less than k minus mu1 over 1 over root n. But what is that? We've determined the value of k that we're using already. We have said this is the value of k that we will use to get alpha as the level of significance. So we're going to put that value of k in here. So this is the probability that a standard normal, let's just write it as z, standard normal is bounded by, here I have this value of k, mu 0 plus z alpha over square root of n, that was k, minus mu 1 over 1 over root n. That's the power of this test. That's 1 minus the power of this test. That's the probability of a type 2 error for the test when we set k to be the k which gives us a level of significance alpha. Does that make sense? So it's slightly different than the previous question. It's not what value of k should we take to get beta. It's given the value of k that we took from wanting our level of significance to be something, what is the resulting power given the value of the alternative hypothesis, given the value of mu1 for the alternative hypothesis? Does everybody follow that logic? Should I write that down in words? Why don't I write that down in words? So recap. K was chosen to give a critical region, the place where we're going to accept or reject the null hypothesis, of size or of level of significance, alpha. So first we chose K. Once K is chosen, what is the power of the test? Then the power of the test is 1 minus beta, where beta is this, where beta is the integral from, let's simplify this a little bit, mu 0 minus mu 1 times root n plus z alpha, bless you, to infinity of a standard Gaussian norm, e to the minus u squared over 2, 1 over root 2 pi. So first we chose a value of alpha. We solved for k given that value of alpha. So k is a function. So k is a function of alpha and mu 0. Right? Remember what k is. Well, it's right here.
Wait, so,
and n.
Is beta the probability that z is less than something or greater than something?
Say it again?
Is beta the probability that z is less than something or greater than something?
Sorry. Thank you. Other way around. Let's put a minus infinity and a minus sign. So it's for minus. It's that z is less than something. Thank you. Wrong way around. Okay. So let's figure this out. Let's do an example that I think might clarify this. So you see, k is a function of mu 0 and alpha. It has nothing to do with mu 1. It's not a function of the alternative hypothesis. Beta is what's going to tell us whether the alternative hypothesis is whether this test will be powerful, how powerful this test will be, for determining whether mu 1 is a good value. So now let's do an explicit calculation. So let's say, so here's a question: how many n to test if we want beta less than 0.06 for mu 0 equals 10, mu 1 equals 11. How many trials do I need to run of this experiment? I've already selected alpha as 0.05, so that my level of significance is 5%. So the confidence that I have correctly rejected H0 is 95%. Where mu 0 is 10, mu 1 is 11. I'm going to test the mean as being 10 against the mean being 11 with a variance of 1. So that's a significant distance. If I want to get beta down to 0.06. Okay? So if I want beta down to 0.06, this value, so here's my Gaussian. Now it's a standard normal Gaussian. It's meant to be standard normal Gaussian. And I want this integral from minus infinity up to this value to be 0.06. So what is this value? Well, by symmetry, it's the same as the value on the other side. On this side, it's z.06. So on this side, it's just the negative of that. So this is negative z.06, negative z.06. Right? This probability is the integral from minus infinity to this thing, and I want that to be 0.06. Z.06, you look up. Z.06, bless you, is 1.555. Doesn't matter, let's call it 1.5, with a minus sign. So this thing needs to be this. If I want beta to be 0.06, then this thing needs to be negative z.06. In other words, mu 0 minus mu 1 times root n plus z alpha needs to be negative 1.5. So let's write that down. Mu 0 minus mu 1 times root n plus z alpha needs to be negative 1.5. Or less, if I want to capture a smaller value of beta. What is mu 0 minus mu 1? In our example is negative 1, so this is negative root n. Z alpha, alpha was 0.05. The z of that, z of 0.05 is 1.6. Yeah, 1.645. All right, let me put the 5 5s in there. It'll actually make the, miraculously will make the calculation a little easier. Is equal to negative 1.555, or less than that. So let's put the less than sign, right? Because I want to catch not just beta equals this, but any smaller value will give me an even smaller beta. So I bring this to this side, bring that to that side. I get root n needs to be at least 1.645 plus 1.555. I'll let you do that at home. It's 3.2. And 32 squared is about, 32 squared is 1,024. So this is 10.24. So take n equals 11. Let's recap this calculation. How many times do we need to test, how many samples do we need if we want a level of significance 0.05 and a power of 94%? The power is 94% when we want to test the hypothesis that mu 0 equals 10 against the alternative hypothesis that mu 0 is equal to 11. So we compute what beta is. It's this integral. We want beta to be less than 0.06. Z of 0.06 is 1.55. We're on the other side, so that's the negative. So we want this thing to be less than negative 1.55. What is this? Well, this is my negative 1. This is some number. You bring this to that side. You add the two together. You bring this to the other side. Root n is at least 3.2. Take n equals 11, and you will have the power that you want with the level of significance that you want. Any questions? Okay.